When we looked a little at high school level Newtonian gravitation in the last two videos, numbers 1 and 2, we realised that, successful though it was for most situations, there were a number of confusing issues that arose within Newton's theory and also from it. The first one was that the concept of mass seems to embody two very distinct properties which, at least in the Newtonian sense, seem to be unrelated. One of these, inertial mass, has to do with the difficulty of changing the motion of an object, and the other, gravitational mass, relates to how that object gravitationally attracts other masses. Secondly, the definition of weight as the force of gravity on an object implies the idea that weightlessness should be the absence of such a force, and that seems perfectly sensible. However, the sensation of being weightless seems to be experienced in situations where there is a Newtonian gravitational force, such as when things are in orbit or in free fall, and indeed the word weightless is used to describe such situations. There seems therefore to be something inconsistent with this way of thinking. Thirdly, gravitational fields are never really uniform fields. They always converge towards an object which has mass. This is not a problem in itself, except that a uniform or constant acceleration seems to mimic an extra force of gravity, and yet the apparent gravitational field that the acceleration produces is uniform. It has parallel, equispaced field lines. And if we want to suggest that a constant acceleration is equivalent to a gravitational field, then there's a problem. And so we come to the brilliance of Einstein. In forming the equivalence principle, which was discussed in video number 2, he realised that any new theory of gravitation which would mathematically describe the gravity-acceleration connection would need to involve geometry. This geometry will ultimately be the geometry of four-dimensional space-time. And space-time is something which Einstein's special theory of relativity had already introduced, but that theory had deliberately avoided accelerations. It had focused on what is termed inertial frames, measurement systems moving at constant velocity relative to one another. In his later general theory, however, Einstein introduced the idea of frames of reference which could be accelerating with respect to one another. This inevitably brought gravitational ideas into space-time, and consequently the need to adjust what you might call the shape of space-time so that the switchover from constant acceleration with its parallel lines to gravity with its converging lines could be made within the theory. All of this also led to the idea of the curvature of space-time, and that is where we're heading. However, a sensible way to approach the whole thing is once again to keep any velocities well below the speed of light initially, and also, for the time being, to ignore time. In other words, we will first consider only space and not space-time. This will make the initial concepts more manageable, and the idea of space-time can then be introduced later. Our starting point will be to look at some ideas relating to Riemannian geometry. In one sense, the mathematics of this will not be too difficult, but there is so much of it that it can be mind-boggling. In order to try and cope with it, a new shorthand will be introduced, such that the equations then look simpler. But of course you have to understand the shorthand in order to appreciate it, or the whole thing can seem even more confusing. For simplicity as a starter, let's consider various spaces of different dimensions. For example, I'm sure most people watching this have already thought about what a one-dimensional space might look like. I'll start by showing such a thing as a straight line with finite thickness. Even though there is really only one dimension, the x dimension, there's no y and there's no z, and there's really no thickness. If we play the game of imagining beings that could occupy such a space, we'll probably think of them as being points, which we'll illustrate as this red dot. And they could presumably move around on the line, or we might think of them as line beings, which could also move backwards and forwards along the line. No overtaking is allowed in this one-dimensional space. We also probably find it easy to conceptualize the idea of this space being bent slightly in some way. Now be aware I'm avoiding the word curved or curvature at this point because those words have a special meaning which we'll come to later. Let's just imagine gently flexing the dimension, like gently bending a thin piece of wire. No other distortion is involved. This kind of bending is easily returned to a state where it's seen as a straight line again, and there's no distortion involved at all. As we'll see later, we restrict the use of the word curved to a very different kind of thing altogether. Anyway, to illustrate this bent or flexed space, we would simply have to introduce a second dimension in which to bend this one dimension into, and it might look something like this. In this case, we'd say that our one-dimensional X space is embedded in the two-dimensional space of the screen, but it's still a one-dimensional X space. Remember, the so-called line has no thickness. It's not really like a piece of wire. There are no internal tensions within it when it's bent. This kind of bending could be described as extrinsic curvature in the sense that intrinsically the space itself is not curved. It's not been stretched in any way, but has simply been shown as being flexed into an extra dimension. You'll see later that with intrinsically curved spaces, the properties of those spaces are very different indeed. However, with this kind of one-dimensional space, which I'm calling flexed or bent, any so-called beings living on that surface would not be aware of the second dimension, the up and down of the screen here, or indeed of any bending or flexing of it visually. To them, there would still only be two ways to go, backwards and forwards. The bending, even of them on the line, if they were line beings, would not be sensed at all. This is a one-dimensional space. You can only go in a straight line, either backwards or forwards. Yes, a straight line as far as the so-called beings are concerned, even though it looks bent to us who have the benefit of sensing the second dimension, the y direction of the screen in this case. Again, we're choosing not to use the words curved or curvature, which have a special meaning and which will be discussed later, even though this could legitimately be called extrinsically curved. This bent line is exactly the same as this straight line as far as the geometry is concerned. The measured distance apart of 2 points is the same, whether or not the dimension is flexed. Both of these spaces are what we would call flat. Yes, I know it's a bit confusing at first. One is straight and the other is bent in some way, yet they are both called flat. This will hopefully become clearer later, but a simple way to think of it for now is that in neither case, straight or bent, is there any real distortion or stretching of the line. Again, it relates to this special word curved, which we haven't discussed yet. We should say at this point that although we often find it convenient to draw it as a finite length like this, and will often put artificial limits on it for convenience, strictly speaking, this line goes off to infinity in both directions. This particular one-dimensional space is infinite. We should also say, however, that it is possible to have one-dimensional spaces that are not infinite. If, for example, the bending, and I won't say curving, if the bending is such that the dimension comes back on itself, then we'd have what we would call a finite one-dimensional space. So-called beings in this space would still think of it as a straight line, there being only two directions in which to go, backwards and forwards. It's just that if they kept on going forwards, they'd arrive back where they started. Again, they would not sense any second dimension, any y direction. To them, travelling along the line would be analogous to what a spot on an oscilloscope screen seems to do. Moves forward, and after a while passes again through the point where it started from. Also, it should be said that this finite one-dimensional space here is exactly the same as this finite one-dimensional space, providing the length of each is the same. And that's because the bending or flexing is not really an issue. These are each finite one-dimensional spaces, and they are flat. There's no perception of the y direction within the spaces. Different finite flat one-dimensional spaces, such as these, are only really distinguished by their length. However, We will stick to discussing infinite spaces, and we'll look in more detail at the infinite one-dimensional space in a moment in order to consider some other important ideas about vectors. But before we do that, let's now quickly consider a two-dimensional space. In this case, of course, we can use the two dimensions of the screen, x and y, to illustrate the space. And to be consistent with what we introduced in the last video, we've shown it here as x1 and x2, where x1 is the x direction and x2 is the y direction. Just as we drew the one-dimensional space as a finite straight line initially, this two-dimensional space here has been bounded by the outer rectangle, but you should realize that it is an infinite space, extending both positively and negatively in the x1 and x2 directions. You should also assume that it is flat, which is what it certainly looks to be in this visualization. You may be beginning to realize that the word flat also has a special meaning here, but for our purposes at the moment, let's just say there are no distortions in the surface, in the space. It looks flat, it is flat. We could once again play the game of imagining beings that could occupy such a flat plane, and we'd probably imagine them as little areas which can move around anywhere in the space in the two directions x1 and x2. On top of that, we could also imagine the space being bent or flexed slightly in some way, like this. Again, we're avoiding the use of the word curved. There's no stretching or distortion here. This bent space can be thought of as a sheet of thin metal which has been gently bent slightly and could easily be made to return to its unbent state. I don't want to say return to being flat because it is flat, even when it's flexed like this, in the sense that we're using that word flat. Remember also that the space has no thickness, so that when flexed, it's not under any tension in the same way that a piece of metal might be. In order to illustrate what I'm calling this bent flat space using this picture, we've obviously had to introduce a third dimension, the z or x3 direction, into and out of the screen. And as we only have a two-dimensional screen, this third dimension can only be perceived in the perspective of the drawing. If we were doing a demonstration in the laboratory, we could show that the two-dimensional flat space is now embedded in a third dimension. However, here we can only illustrate the third dimension by the use of perspective in the drawing. Remember that the observers in this space cannot sense the z direction, the x3 direction, into and out of the screen in any way. What we're suggesting is that both of these diagrams represent two-dimensional spaces, and assuming no distortion took place in the bending of the second one, they are both flat in the sense that we will be using that word, and which will be explained more fully later. If we were to place an identical rectangular plane object on each surface like this, then it might well look to us, with the benefit of our third-dimensional view of things, that the shapes were different to one another. In fact, they are identical. Observers in the spaces would not sense any difference between the two situations. For example, looking at the version of the space on the left, an observer there could use their measuring instruments to measure the height and width of the shape, as well as the 90-degree angles of the corners. Similarly, observers in the space on the right, who tried to measure this area, would lay out their rule here for the height and here for the width. This width measurement for them would appear to be from a straight line, not curved. Remember, they don't sense the x3 direction at all, and they would get exactly the same answer for width, height and angles as would the observer in the space on the left. Observers in what I'm calling the bent space would not see or experience the third dimension. To them, there would still only be two independent directions in which to travel, x1 left and right, and x2 up and down. The bending of them and their measuring stick would not be sensed at all. This space could be said to be extrinsically curved, although I'm trying to avoid the use of the word curved here, and we'll keep it until we are looking at genuinely intrinsically curved spaces. When we do look at such spaces, and look at what we will simply call curved space, things will not be quite so straightforward. However, both of these spaces here are what we would call flat. Any distances between points in one space would be the same as distances for similar points in the other space. Furthermore, it's possible to bend or flex such a flat two-dimensional space back on itself in one of the two dimensions, and that space would still be what we would call flat. To our eyes, as outsiders with the access to the third dimension, it would be a kind of tube. If an observer in the space, or should I say on the space, moved in a straight line on the surface, they might well end up back in the same place, or perhaps near to the same place. However, they would have no sense of the third dimension, the x3 dimension in and out of the screen. They'd think they were on a flat plane moving in a straight line and then ending up back near to where they started. It could seem very confusing. With this diagram, of course, the x2 direction or y direction could be infinite, so we'd have a kind of infinite tube from our perspective and a strange flat surface for those two-dimensional beings living on the surface. And we could do the same for flexing it around in the other dimension, giving us a flat surface which this time looks like a horizontal tube, which of course could go on in the x1 direction to infinity. Okay, so that's all very well for one of the two dimensions coming back on itself, either the x1 dimension in our first example or the x2 dimension in the second. But could it be both at the same time? Could both directions bend back on themselves for this two-dimensional surface? Well, yes, they could, but things would then be very different. Imagine starting with a finite-sized two-dimensional flat surface bent around in the x direction. From our perspective, it would be a vertical tube like this. This is a flat space, which means that any occupants of this space who made measurements of things would get exactly the same results as if the tube were unrolled, if I can put it like that. Now try to imagine bending the ends of this tube so that they smoothly meet in the middle like a dome on each end. This would not be simply a case of gently bending the sheet. There would have to be tremendous distortions in it to get a smooth dome. And if this could be done, it would still be a two-dimensional space or surface, but these ends would have what we can now call curvature. They're not just flexed surfaces, they are distorted, stretched and squeezed to make the smooth dome. So this part is still flat, but this is not. This part of the two-dimensional space is curved, a word which has special meaning in our study of surfaces and which will be discussed in more detail later. Again, before we go back to looking at more details in one dimension, let's briefly think about things like this in 3 dimensions. We can illustrate this fairly easily like this, where the boundary for drawing purposes has been shown like a box. It's obviously drawn here in 2 dimensions, the plane of the screen, but we have the benefit of perspective to help us to visualize the 3rd dimension, the z or the x3 dimension, out of the screen. We could, of course, illustrate this 3-dimensional space with a model of some sort, actually in 3 dimensions, a physical 3D model in the laboratory. Also, if we were discussing it, we would probably say that although it is boxed in, as it were, for illustration, we're really talking about a space that is infinite in all 3 dimensions. What we can't do, however, is illustrate any kind of bending or flexing for this 3-dimensional space. We can't show bending here in the picture of the screen. Neither could we illustrate the bending of a physical 3-dimensional model. When we had a 2-dimensional space drawn on the 2-dimensional screen and we wanted to illustrate the bending of it, we had the benefit of perspective within those 2 dimensions, and this helped us to see the bending into the 3rd dimension. The perspective there gave us a feel for the fact that the 2-dimensional space could be said to be embedded in the 3 dimensions, and hence any bending could be visualized. However, even with a physical model of the 3-dimensional space actually in 3 dimensions, we have no equivalent of perspective which might help us to see a 4th dimension, which in turn would have helped us to appreciate any bending of the 3-dimensional space. Because of this, I'm sure you realise that it's important that we transfer the concepts which were fairly clear in 1 and 2 dimensions to the situation here where we're dealing with a three-dimensional space. It's important that we believe that the same principles will apply in 3 dimensions as did apply in 1 and 2 dimensions. For example, if for some reason I knew certain details about this three-dimensional space, I might be able to say with certainty that it is flat. Now, if you've never studied any Riemannian geometry, that might seem a strange use of the word flat to you. What does it mean for 3 dimensions to be flat? Well, it's obviously not a flat surface in the normal sense that we would use the word, say for a flat sheet representing 2 dimensions. And yet, just as a one-dimensional space can be flat when it has certain properties, and a 2-dimensional space can be flat when it has certain properties, so, by analogy, a 3-dimensional space can be said to be flat when it has certain properties. Taking the analogy further, just as a one-dimensional space can have a bend or flex in it and still be called flat, and a 2-dimensional space can have a bend in it and still be called flat, so by analogy, a 3-dimensional space can have a bend in it and still be said to be flat, even though we have no way of illustrating it or even imagining it. Crucially, for our later considerations, the same applies to what is called curvature or intrinsic curvature. Now, we haven't really discussed this yet, but perhaps we should at this stage take a naive and temporary definition of curvature and say that it is when a space has a distorted bend in it from stretching it or compressing it. Now, that is far from an accurate definition of curvature, but it will do for now. A truly curved one-dimensional space cannot be said to be flat on account of the fact that the bending in it, as appreciated via the second dimension, has that kind of distortion to it. Take, for example, this one-dimensional flat space shown here by a straight line, and imagine placing 2 markers on it, A and B, here and here. Now stretch the middle section so that A and B remain in the same places from our outside view of it. In order to do this, the stretched section will have to be visualized in the second dimension, the y or x2 dimension, upwards here, and yet it is still a one-dimensional space. Now, this is not just a simple bend which could easily be straightened out. This space cannot be made flat by some sort of coordinate transformation, and so we say that it is not flat. Rather, it has curvature in it, at least in that middle section. As you'll appreciate later, this may well affect measurements and physics experiments performed in the curved region by occupants of this one-dimensional space. Distances will be distorted in some kind of way. Similarly, of course, a 2-dimensional space which is curved, according to the crude definition given a moment ago, cannot be said to be flat. Again, because the shape, as appreciated by the outside observer with the advantage of the third dimension, would not be just a simple bend or flexing. Here is a simple bend in one of the dimensions, the x2 dimension, of a 2-dimensional space. This space is flat, in the sense that we now mean that word. There's no distortion, just a simple bending or flexing, and this could easily be straightened out to look flat from our 3-dimensional viewpoint. Here, however, is some curvature introduced into that 2-dimensional space. I hope you can see the perspective here. There's a kind of distortion or stretching. In this case, that stretching is into the same extra dimension that the bending was in, but it means now that the space in that region is what we call curved. Clearly, the x1 direction here, left and right, has not been distorted, and is also in fact not flexed or bent in any way either. We could, of course, introduce curvature in both of the directions. For example, if we started with a flat, unbent 2-dimensional space and stretched or compressed it somehow in both directions. What we would have to do is to take our finite 2-dimensional flat space. In fact, for convenience, let me make the artificial boundary a circle like this and look at it with some perspective. It's still flat, and as it happens, unflexed or unbent, but that's immaterial. It's flat, And after this tilting, we would say that its two dimensions are x and z, or x1 and x3. If, however, we then stretch or distort both the x1 and x3 directions, say into the x2 direction, upwards in the y direction if you like, we could make it into a dome, a convex surface, a kind of bulge. A metal worker could do this by hammering and distorting a flat piece of metal into a dome shape, and in that case the metal would be thinner in most places. But obviously there's no question of thinning with our two-dimensional space, but it would certainly be stretched and distorted in a situation like this. What we have here is a two-dimensional curved surface. It cannot be made flat simply by straightening it out. It is, in a sense, distorted. In terms of the language we're moving towards using, this two-dimensional surface is curved. Before we try to think about three-dimensional curved surfaces, it's probably worth looking a bit more at this type of two-dimensional curved surface. Once again, any occupants of this surface would only be aware of two dimensions. They would not immediately be conscious of the curvature. To them, the surface would ostensibly appear flat, at least in our everyday use of the word. However, once they did some measurements or physics experiments, they would soon realize that this could not be true. Even though they cannot sense the third perspective direction that we, as outsiders, are aware of, they could know from their experiments that the surface they are living on is not flat in the sense that we are now using that word. Consider, for example, this situation where we have a curved two-dimensional space which happens to look to us like half a sphere. Someone on this surface could draw what they see as three straight lines to form a triangle. Those lines would be dead straight as far as they were concerned. However, with our advantage of the perspective of the third dimension, the lines would look like they were arching in a circle along the curve of the surface. They see a triangle, and we see a kind of curved triangle. The crunch comes when they measure the internal angles of their triangle and add those angles up. The result that they would get would be a number greater than 180 degrees. And this is because of the curvature of their two-dimensional space. In fact, some triangles drawn on their surface like this one could even have combined angles as high as 270 degrees and would contain three 90-degree angles. That would be obvious to us as outside observers who can see the third dimension, but to the occupants of the space it would simply be a strange result. So that's a very brief look at curvature in two dimensions. When we now move to thinking about three dimensions again, all the principles of what has just been discussed will have to be applied to the three-dimensional space, but without the benefit of any clear three-dimensional illustrations or pictures. For example, if we had a genuinely curved three-dimensional space, then it cannot be said to be flat. And yet we have no way of picturing any curvature. We can't see the fourth dimension to appreciate any distortion or stretching any curvature. We have to, and we do talk about three-dimensional spaces which are flat and others which are curved. And in order to make sense of this, it's important that you're able to refer back in your mind to the two-dimensional case in order to hold on to the concept. We can't really draw or model curved three-dimensional space, although some people have made attempts to do so. It's probably better for us if we take the attitude that because we hopefully felt comfortable with the concept of curved space in two dimensions embedded in a third dimension, then it must be possible to have curvature in a three-dimensional space which we might consider to be embedded in a fourth dimension. I'm sure by now you're realizing that we wouldn't really talk much about a simple bend or flexing in three-dimensional space. That space would be flat, and we can't visualize the bending anyway, so what's the point? It's far more important for where we're going that we're able to discuss three-dimensional spaces which are either flat or curved, unstretched or stretched. And as I say, a more rigorous definition of the word curved will be given later. This difficulty of visualizing a perspective for three-dimensional space, in other words, a fourth dimension, will be why most discussion of Riemannian geometry and later even of general relativity will be done using illustrations of two-dimensional space or even of one-dimensional space. The assumption will be that we can then, at least mathematically, step up any conclusions to 3 dimensions. So as we work through some of the mathematics, we'll do a lot with pictures of two-dimensional surfaces, some flat, with a bent or not, and some curved, and this will then be used by an extension of that mathematics to suggest that a similar kind of thing is relevant to 3 dimensions, even though we can't picture it. Much later on, of course, this will all be applied to 4 dimensions when space-time is discussed, and it will be light that will make up the 4th dimension of space-time. But that's a long way off, and before we get anywhere near to that, let's return briefly to look at a one-dimensional space, and we do this in order to consider some new concepts in preparation for some more involved Riemannian algebra and geometry. My guess is that if you've never studied subjects related to general relativity before, you will never realize that we can think of there being 2 distinct types of vectors which are given the names covariant and contravariant. In what follows, we will simplify the concept into a fairly straightforward idea which will be useful to us, without getting into the mathematics of dual vectors and dual spaces. As you begin to think about this, you will realize that we focus a lot on different measurement systems in different frames of reference, and indeed that will be the connection with general relativity eventually. Consider an infinite one-dimensional space in the x1 direction, the old x direction, and we'll imagine it's being measured using a simple frame of reference, the kind of thing we looked at earlier. Now consider a displacement vector somewhere in that space. You can think of it as the distance between 2 points on the line if you want, but we'll put an arrow on it to signify that we're talking about a vector, a displacement vector in this case, and we'll call it S. The size of the vector will be the distance measure along the line, and the direction, well, it only has 2 choices in this space, positive or negative, and in this case it's positive. It's in the positive x1 direction. Again, we're using x1 with the upper index rather than simply x, and that is to get used to the new way of designating axes, but we really mean the x direction. Being in one dimension, this vector doesn't really have components, or rather, it has one component, which is its actual measured size. Suppose that we now wanted to measure that size, the magnitude of this displacement vector, the one component that it has. Then the obvious thing to do would be simply to put a scale against it, such as a measuring stick, and make a measurement of the distance, or rather the displacement. This red measuring stick or rule is a kind of frame of reference. It's our measuring system for this one-dimensional space, and in this case it looks as though the vector is about 30 units on this red scale. Now let's consider what would happen if we used a different measuring rod for our measurement, one which had its scale stretched, say, to double the size of the red one. We've already talked about stretching space itself. That was in a sense how we approached curvature. We stretched the space itself, but now we're leaving the space alone and stretching the measuring rod for that space. So if we use this blue rule, which is like the red one but stretched to twice the length, then the new measurement length of this same vector would come out to be about 15 units on this scale. The measurement on this blue scale is smaller. It's the same displacement vector, of course. The distance is exactly the same in the space, but the measurement of it has changed from 30 in the old system to 15 in the new, simply because we used a double scale. Now I guess that's obvious, and we don't even need to involve a measuring stick or rule to realise this. We could have imagined that the dimension itself had distance indicators or markers on it. We could have had a red reference frame called x1, to which we could have marked off numbers like this. and a blue reference frame called x1 tilde, which would have had numbers twice as far apart, like this. This simply states the obvious again. We get a size of 30 units in the red frame of reference, and we get a measurement of 15 units with the blue stretched frame for the same vector. A doubling of the scale has halved the measurement of the size of the displacement vector s. All this is fairly obvious. Vectors which behave like this, which measure to be smaller when the scale is made bigger, are known as contravariant vectors. The word contra means against or contrary to, and so the name contravariant reminds us that the measured size of the vector varies contrary to the way the scale changes. If the scale goes bigger or stretches, then the measured value of the vector goes smaller in proportion. Of course, if the scale shrinks, then the measured value increases. In each case, it should be obvious that the vector itself doesn't change. It's the measurement that is contravariant. Another contravariant vector would be velocity. Our picture of things would have to be slightly different to illustrate this, as we would be considering the velocity at a point in this one-dimensional space. This diagram here represents the velocity v of an object at the point x1 equals 0, at the black dot, and it's being measured in the red frame. The green arrow in the picture is there simply to give us an indication of the size of the velocity. It's not in any way spread across from 0 to 30. This kind of distinction has to do with vector spaces, or where the vector lives, for want of a better word. And without getting into all of that, we'll just say that the vector v here is the velocity of some particle at that point, and the arrow and measurement scale are simply there to give an indication of its size and direction. If the object had a larger velocity when it was at a different position on the scale, say here, then we would perhaps represent it like this. You should be able to appreciate, I think, that velocity is also a contravariant vector on account of its direct dependency on a measurement of displacement. The definition of velocity is the rate of change of displacement with time, and the fact that x1, or x, is on the top of this velocity formula means that because any measured x1 value will go down if the scale is stretched, that means that the measured velocity will also decrease. So as with the displacement vector that we looked at, if the scale or frame of reference for this velocity vector is stretched, then the measurement of velocity will be decreased and vice versa. Remember again that the velocity itself at a particular place will not change when the scale is altered. It's simply that the measurement of it will be different on the new stretched scale. Any kind of vector which is produced by having x or x1 on the top of its formula will be a contravariant vector. Another example would be acceleration, a. Okay, so now let's consider the other type of vector that we can have, which is called a covariant vector. We'll start with our one-dimensional frame of reference again for distance x1, and this time I'll put exactly the same equally spaced distance markers on it straight away, those for the red frame of reference, the one before we considered any stretching. Imagine also that within this one-dimensional frame of reference there is a constant gravitational field g throughout it. Such a field is a vector, and of course in this space it will have to be either in the positive or negative x direction. We've only got one dimension after all. Let's assume that the gravitational field we've got is positive and doesn't change from place to place along the line. It is a constant field, the same at every place or point on the scale, at this point here, and here, and here, and so on, everywhere. Don't forget, the arrows here are simply to give us an indication of the size and direction of the field, and are not necessarily related to the scale readings where they happen to be. However, the value of the field obviously does have a relationship to the x1 scale, as we'll discuss in a moment. In order to explain this, rather than have these dots and equal-sized arrows everywhere to indicate the gravitational field vector g, we will instead put in values of the gravitational potential phi. Now you should remember this from video number 1, where we deduced that the gravitational field at any point is given by minus the rate of change of the gravitational potential with distance or displacement. Here, in these reminders of the formula, I've shown the distance measure x1 in red as a reminder that we're using the red scale at the moment. Remember also that little g is the gravitational field strength, or the force on a unit mass at a point in space. And assuming the equivalence of inertial and gravitational mass, this g is also the acceleration of any value of mass in this gravitational field. Whichever way you think of it, g is a vector field. Phi, the gravitational potential, is a scalar. It has no direction, and it is measured in joules per kilogram. This means that little g is in Newton per kilogram, or if you prefer, meters per second squared. The fact that we're saying that the gravitational field g here is constant everywhere means that the gravitational potential must be changing regularly or linearly with the distance x1. We'll make up some numbers for the gravitational potential phi in various places, say at these green dots, and we'll show the values of the potential at these points with these numbers above the line, like this. Phi is 6, 8, 10, and 12. These numbers are increasing linearly to the right, which means that the constant gravitational field g in this particular situation is to the left. This value of 6 for the gravitational potential means that a 1 kilogram mass placed here would have a potential energy of 6 joules. Moving that 1 kilogram to here in the gravitational field, where the value is 8, would need work to be done against the field, and the potential energy of the 1 kilogram mass at this point would be 8 joules. You'll notice that the numbers chosen are, for convenience, such that they do indeed increase linearly with distance, 6, 8, 10, 12, equally spaced apart in space, and so the gravitational field will definitely be constant, and the field will indeed be in the negative x direction. If you like, the rate of change of potential with distance is a positive constant. The positive is increasing with increasing x1 to the right, but on account of the negative sign in the formula, and also logically because of the work done considerations, the gravitational field is constant and in the negative x direction. Now, the fact that the field g is a constant in this situation means that we don't need to bother about doing a differentiation to work it out from phi. The constant field means that we can take any 2 points, say a and b, and we can write the field like this: phi b minus phi a over x1b minus x1a. The change in the potential between the 2 points divided by the change in displacement, with a negative sign added, of course. We could have looked anywhere on this line to do the calculation of the field because the field is constant everywhere. And so with A and B, if the potential is in joules per kilogram and the scale is in centimetres, this bit tells us that the gravitational field G is the negative of 8 minus 6 divided by 0.4 metres, which is minus 5 Newton per kilogram, or minus 5 metres per second squared. Again, the minus sign means that the vector field points in the negative x1 direction. This is the measured value of the constant gravitational field everywhere in this space, as measured by this red measuring scale on the x1 dimension line. In this little discussion, the gravitational field has been measured via a measurement of the gravitational potential. Now, we asked the same question as we did before. What would happen to the measurement of that field vector g if we used a different, stretched measuring scale, say one that had had its scale doubled? The various points in space would keep their same gravitational potential values, but the stretched scale, which we'll now draw in blue for measurements of x1 tilde, would look like this. Notice that the 6 and 8 are in the same place in the space, but they are being measured differently. They're now being measured to be at 0 and 20 blue units instead of 0 and 40 red units. Again, because of the equal spacing of the potentials and hence the constant gravitational field, we can look anywhere on this scale to do the calculation. So if we take the points A and B again, we get for the gravitational field value measured using this blue x1 tilde reference frame 8 minus 6 over 0.2, which is minus 10 Newton per kilogram or meters per second squared. This time the measured value of the field has doubled in response to the scale being doubled. I'm sure you realise that the field itself has not changed. The gravitational field, which is a vector, is the same strength as it was before because the potentials haven't altered and the way they change over space hasn't altered. But it has been measured to have changed because a different scale or frame of reference has been used, and this time the measurement has changed in the same way that the scale did. It doubled. Vectors like this, which measure to be bigger when the scale is made bigger and vice versa, are known as covariant vectors. The prefix co gives the sense of cooperation or going along with or doing the same as. If the scale goes bigger or stretches, the measured value of this kind of vector also goes bigger, in the same proportion. And of course, if the scale contracts, then the measured value decreases as well. Once again, we should stress that the vector itself doesn't change. It's the measurement of it that changes. It's worth noting that whereas contravariant vectors tended to have displacement or x1 on the top in their formula, things like displacement, velocity and acceleration all had x1 on the top. Covariant vectors tend to have displacement on the bottom of their formula, and the one we considered, the gravitational field, was given by minus phi by dx1, where x1 is on the bottom. Another example of a covariant vector would be the electric field E, which in one dimension would be given by minus the rate of change of electrical potential V with displacement x or x1. Again, x1 is on the bottom in the formula, and you can see that if the scale stretches and the measurement of x1 decreases, then the measurement of the electric field will increase. With covariant vectors like these fields, if the scale or frame of reference is stretched or made bigger, then the measurement of the vector will also increase, and vice versa. Now, in discussing the distinction between a contravariant vector and a covariant vector, we did it by thinking about vectors in one dimension. And there was a reason for that. Vectors in one dimension only have one component, and that is essentially their magnitude or size. However, as you'll see later, we will need to think a lot more carefully about this kind of thing when we consider vectors in two or more dimensions. Our consideration in one dimension looked at how a vector's measured size or magnitude changed when the scale of the one-dimensional reference frame was altered. This caused what we might call a transformation, not in the actual vector, but in its measured value. So that when we had a contravariant vector, which I'll call v-con, like displacement or velocity, we found that if the scale was increased or stretched by some factor f, then the measured value decreased by the same factor. We picture this transformation by having the original frame in red with the axis x1 and the transformed frame in blue with the axis x1 tilde. This transformation of the measured size of the contravariant vector v-con could therefore be written like this, where for reasons that should become clear later, I have put the contravariant indication as a kind of upper index con. In this equation we are using blue v tilde within the modulus signs as the measured size of the vector after transformation to the blue x1 tilde frame. This new blue measurement is equal to the old measured size of the vector in the red frame divided by the f, where f is the factor by which the frame has been stretched in changing from red to blue. This is for a contravariant vector. On the other hand, when we had a covariant vector v-cov, such as a gravitational field, we found that if the scale was changed by a factor of f, then the measured value of v tilde, in the new frame increased by the same factor. Again, for our picture of the red frame stretching to the blue frame, this transformation of the measured size of the covariant vector can be written like this, where the cov indication has been put in the lower position, again for reasons which will be later explained. These two equations simply state what we have found for the one-dimensional case. However, if you think about it, this factor f is the ratio of the scale of x1 to that of x1 tilde, one over the other, which in the particular example we discussed happened to be 2. We double the scale. Also, given that there might be situations where the stretching is different in different places, it would perhaps be better to write this ratio f as a differential like this. Here, f is the rate of change of the x1 scaling with respect to the x1 tilde scaling. I hope you realise that it will be useful to have this differential version of the scaling factor, because one can perhaps imagine having the transformed frame of reference, the blue tilde frame, stretched and compressed in different ways at different places. For example, it could go from this straightforward linear red measuring system to be transformed to this rather strange blue frame. In this particular blue frame, parts of it have been stretched by different amounts, and some parts have even been compressed, meaning f in that region is less than 1. In a situation like this, vectors at different places would need dividing or multiplying by different conversion factors, and that's when the idea of the differential factor would come into play. Remember that in general, vectors are considered to be at a particular point in space. A particle has a velocity at a particular point, or the field has a value at a particular point. We only draw them as extended arrows for visualization. For completeness then, here are the formulae for the conversion of the measured sizes of contravariant and covariant vectors at a particular point in space when the red x1 frame of reference is transformed to the blue x1 tilde frame. For a contravariant vector at a point in space, the measured size in the new tilde frame is equal to the value in the original frame multiplied by the gradient dx1 tilde by dx1 at that point. For a covariant vector at a point, the measured value in the new blue tilde frame is equal to the value in the original frame multiplied by dx1 tilde at that point. It should be obvious that we have a similar pair of equations for doing the conversion the other way round, for converting from the blue x1 tilde frame to the red frame. But you don't really need these, as long as you remember the rule for the way up that the differential should go. In crude terms, for contravariant vectors, the dx on the top must be what you're converting into, whereas for covariant vectors, it must be on the bottom. Now, although we won't actually use these equations very much, they are important. In particular, they'll be used at one stage later to justify our labeling and description of the various types of components of vectors in more than one dimension. When we look at vectors later, any types of vectors, and they're in 2 or 3 or more dimensions, we will think about different types of components that the vectors can have. And in naming these various types of components, we will make use of these two formulae, and then we'll probably forget about them. And hopefully that will become clear later. Just hold these ideas and these formulae as simple facts for the moment. You don't really need to remember all the detail. In one dimension, we can think of there being 2 distinct types of vectors, contravariant and covariant, and the measured size or magnitude of them responds differently when the frame of reference is stretched or compressed. The vectors themselves don't change, but their measured size does. This means that if we had various kinds of vectors at some point in space, then the way they would respond to the stretching of the frame of reference is essentially via the differential rate of change of one frame with the other at the particular point. Contravariant vectors have to have their size measurement multiplied by the differential one way up, and covariant vectors have to be multiplied by it the other way up. And as I say, that fact will be useful later. In the next video in this series, we will begin to look more into two-dimensional spaces. We'll look at frames of reference other than Cartesian coordinates, and this will lead us into thinking more clearly about the various components of vectors, and also why we sometimes give them upper indices and sometimes lower indices. The justification for one or the other will be given, and will lead to a new and appropriate way of expressing the various formulae about vectors. This video number 3 has been an introduction to Riemannian geometry, and in particular we discussed covariant and contravariant vectors. In the next video, number 4, we will begin to think about contravariant and covariant components of vectors in 2 dimensions, and that will lead to a concept of the metric tensor.